These are the examples for Lesson 2-2, Conditional Statements. In this video, you will use deductive reasoning by writing conditional statements and their various forms. You'll also learn to determine the truth values of conditionals, write counterexamples based on deduction, and learn to use the language of logic. Example 1. In this example, you'll learn to identify parts of a conditional statement. Identify the hypothesis and conclusion of the following conditional statement. If an animal is a robin, then the animal is a bird. We know this is a conditional statement because there's two parts to it, and especially since we have the word if, a qualifier word that gives us a condition. Well, the condition in a conditional statement is called the hypothesis, so this right here is the hypothesis, whatever comes after the if, basically, as a sentence. So P, lowercase p, is used for hypothesis in the language of logic. So P is an animal is a robin, period. Then for the conclusion, we use lowercase letter q, and it's what immediately follows the word then, the conclusion to that conditional statement right here. So the conclusion Q is the animal is a bird. And there you have it. Example 2. In this example, you will learn to write a conditional statement in if-then form. You'll determine truth values and use logic symbols. So this one says, write the statement below as an if-then conditional. Then state the truth value of the conditional that we write. And then finally, we're going to write the conditional's converse, but in symbolic form. So here we go. Angles that share a vertex must be vertical angles. There's no if or then in this conditional statement, so we place them in there. There's two parts to the sentence: angles that share a vertex, and those angles must be vertical. So first part is our qualifier, so we write if angles share a vertex. Comma, and then the conclusion, then, reading this again, angles that share a vertex must be vertical angles. So if angles share a vertex, then they, which means the angles, or refers back to the angles here, must be vertical angles. We've just written the conditional in if-then form. Now we need to determine whether this is, or write it in logic form. So, or the truth value, truth value. If angles share a vertex, then they must be vertical angles. Okay. Remember, the vertex of an angle is the point at which the two rays come together, forming the angle. So if there's any way we can have a situation where we have a vertex that's being shared but the angles are not vertical, then this would have to be false. And here's one right here. Remember, vertical angles are angles that are opposite each other, like this. Angles 1 and 2 are vertical angles. I just show you that because that's what this is implying. However, if two angles share a vertex, like angle 1 and 2 here, they share the same vertex right here, and yet these are not vertical angles because the angles are not formed by two lines that intersect. They're only formed by this line, this ray, and that ray. So this would be a counterexample. We'll get to that later. But the point is, this is a false statement because if it's false anytime, then it's false all the time. This was if P then Q. The hypothesis then conclusion. So this was if P then Q. in logic form. So to write the converse, we simply reverse the Q and the P, and we start with the Q, or the conclusion. If the conclusion, then the hypothesis P. Now, they didn't ask us to write the converse out, but this is what you would use to write it out. Example 3. In this example, you'll identify parts to the conditional and determine a counterexample if the conditional is false. And here we go. They want us to underline P, the hypothesis, and circle Q, the conclusion, for each. Is the conditional true or false? If it is false, find the counterexample. A. If a woman is Hungarian, then she is European. Okay, so they want us to underline the hypothesis, which is P, and circle the conclusion, which is Q. So after the word if, we have a woman is Hungarian, up to the word then. So we underline the hypothesis right here. Then she is European. Okay, so after the word then, she is European. That statement right there should be circled. Is this false? Well, to determine that, you have to know where Hungary is. Hungary is in Europe. So if a woman is Hungarian, then she is European is true. B, if a number is divisible by 3, then it is odd. Same thing, we have if and then, so we have a conditional. The part after the word if is a number is divisible by 3, so that statement right here is the hypothesis. The conclusion is anything that comes after the word then in the sentence, so it is odd. By the way, what is it? It is referring back to the number. A bit of English there. Okay, if a number is divisible by 3, then it is odd. So this would be an example of what they're talking about. This 9 divided by 3, that's what divisibility by 3 means. You can divide by 3 and you get a whole number as a result. 9 divided by 3 is 3. And since it's divisible by 3, they're saying that this number right here has to be odd. And it is here. 9 divided by 3 is 3. 9 is odd. Can you come up with a counterexample? If we can't come up with a counterexample, then this is true. What about this? 12 divided by 3. That's divisible by 3. 12 is, because we get 4. But 12 is not odd. So our counterexample, this is false. Counterexample would be 12 is even and it's divisible by 3. That counters this statement, which makes it false. 12 is even and yet it's divisible by 3. Example 4. In example 4, you'll learn to write all forms of a conditional statement and write counterexamples for false statements. Now, before we start, sometimes it really helps when you're trying to understand the concept of a problem like this, figuring out which is true, what's false, is to go a little further with it and actually write examples for the statements that are true and not just counterexamples for the false ones. So I'll probably be doing that a little bit here. Example 4, what are the converse, inverse, and contrapositive of the following conditional? And here's the conditional. If a figure is a parallelogram, then the figure is a quadrilateral. Then they ask, what are the truth values of each? Remember, the truth value of a statement is either true or false. If a statement is false, give a counterexample. So there's quite a bit to do here. Let's go ahead and start by identifying the hypothesis and conclusion of this conditional statement right here. Now remember, this is the conditional statement they gave to us. I'm just going to go ahead and write if P then Q, so we can at least have logic symbols going with it too. The sentence or the phrase after the word if is a figure is a parallelogram. So this is the hypothesis. A figure is a parallelogram. Period. Then after the word then, the figure is a quadrilateral. That's our conclusion. The figure is a quadrilateral. Period. Okay, well, let's see if this is true or false. They did ask us to find truth values for all of them. So, truth value. If a figure is a parallelogram, then the figure must be a quadrilateral. Sometimes it helps to put a word like must in there to help you see clearly what you're looking at for true and false. Well, if a figure is a parallelogram, if you'll recall, a parallelogram is a four-sided figure in which both pairs of opposite sides are parallel. Remember, that's the symbol for parallelism in two lines. And so those two sides are parallel and these two sides are parallel. So what they're saying is, if you have this, a parallelogram, then it automatically has to be a quadrilateral. Is that true? Yes, it is. It's got four sides. That's what a quadrilateral is. It doesn't matter how the sides are formed and whether they're parallel or not to each other. It has four sides, so it's true. The converse is from if P then Q would be if Q then P. We just reverse the P and Q. So we do that with the actual sentence. So instead of this conditional, we reverse those and we get if the conclusion. The figure is a quadrilateral, then the figure is a parallelogram. Okay, so we wrote it. That was one of the things they asked us to do. We've got our symbol here to help us stay on track. Now let's find the truth value. If a figure is a quadrilateral, then it must be a parallelogram. So what they're saying is, if we draw just a quadrilateral, it's got to look like this. It's got to have both pairs of opposite sides parallel. Is that true or false? It's false. Can we come up with a counterexample? Well, there's several that we could come up with. The one that comes to my mind is a quadrilateral that's in the form of a trapezoid. And a trapezoid has one pair of opposite sides that are parallel, like this one. So, trapezoid. Another possibility would be a kite. A kite is not a parallelogram. Squares, rectangles, rhombuses, those are all parallelograms, so we couldn't use those. But another one, we could just draw a quadrilateral that has no specific side lengths or parallel sides at all. That's still a quadrilateral, so there's a bunch of counterexamples. And for the inverse, we go back to the original conditional, if P then Q, and we negate both parts. We don't reverse them, but we negate them. So instead of if P then Q, we come down here to inverse, and it's if not P, then not Q. So that means we're going to start with our hypothesis here. A figure is a parallelogram, and negate it. So that would be if a figure is not a parallelogram. Then our Q, or conclusion, the figure is a quadrilateral, we negate it. Then the figure is not a quadrilateral. Now let's see if we can figure out the truth value of this one. If a figure is not a parallelogram, then the figure cannot be a quadrilateral. Think about that. If a figure is not a parallelogram, then it couldn't be a quadrilateral. Is that true or false? That's also false. Because it's a lot like this one in a way. If a figure is not a parallelogram, it doesn't necessarily mean it's not a quadrilateral. For instance, here is a quadrilateral, but it's not a parallelogram. So we satisfied the hypothesis. This figure is not a parallelogram, but then they said then the figure is not a quadrilateral. Well, this is a quadrilateral, so this is false. Finally, the contrapositive. You go back to the converse and you negate both parts of it. So instead of if Q then P, we negate both of them. We don't reverse them. And that would be if not Q, then not P. So that means we have to come back to our converse and reverse those two. If the figure is a quadrilateral, instead of that it'll be if the figure is not a quadrilateral, then the figure is not a parallelogram. Okay, truth value. This is the counterexample for that one. Okay, for the truth value on this one, if a figure is not a quadrilateral, that means it can't have four sides, then the figure is not a parallelogram. Well, that's true. It can't be a parallelogram. If a figure is not a quadrilateral, let's say it's a triangle, then there's no way that can be a parallelogram, because a parallelogram at least has four sides. So this would be an example, which they didn't ask for, but it sometimes helps to look at that sort of thing. Example 4. Example 5. In this example, you'll learn to translate conditional statements and logic symbols to their equivalent statements written out word for word. Here we have example 5. P is defined as the statement, the game is tomorrow. Q is defined as the statement, the team prepares for the game today. Write a conditional statement given each symbolic statement. Then after you complete all four of these, choose the conditional that seems most unlikely to happen. So let's concentrate first on writing these, and then we'll go back. If P, then Q. That's the conditional. So since P is here, we write if the game is tomorrow, comma, then Q. Then the team prepares for the game today. I'm just going to write then they prepare for the game today. If the game is tomorrow, then they prepare for the game today. Or if the game is tomorrow, then the team prepares for the game today. Either way. B, if Q, then P. So this would be the converse. So we simply switch these in their order. So if, instead of the game is tomorrow, if the team prepares for the game today, comma, then P, the game is tomorrow. The C, part C. This says if P, then not Q. We don't have a name for this. They just asked us to write it in this form, so we got to be careful here. If P, which is this statement right here, if the game is tomorrow, then not Q. So then the team does not prepare for the game today. D, if not Q, then not P. Can you recognize which form this is from the original? Yes, it's the contrapositive. So we take the converse and just negate both parts to it. So if the team prepares for the game today, instead of that, we negate it. If the team does not prepare for the game today, then not P. Not P would be, instead of the game, then the game is tomorrow, we have then the game is not tomorrow. Okay, now after you've written all four of those, go back through, figure out which one is most unlikely to be realistic. If the game is tomorrow, then they prepare for the game today. That makes total sense. You're going to prepare for a game tomorrow, you want to practice today. B, if the team prepares for the game today, then the game is tomorrow. Well, that could be true, but whether it's true or false, that seems pretty rational. C, if the game is tomorrow, then the team does not prepare for the game today. Well, I would think if you have a game tomorrow, it would be a good idea to prepare today. So this is probably our answer to which one is most unlikely. D, if the team does not prepare for the game today, then the game is not tomorrow. That's not necessarily true, but if it's not tomorrow, then not practicing today may not be too bad. So C is the one that's most unlikely. Example 6. In example 6, you will learn to draw and label a Venn diagram. And we have two statements. Venn diagrams can be used in conditional statements, but always remember that in a Venn diagram for a conditional statement, so there's always one subset, and there could be more than one subset, but I doubt in this particular level that we're going to have more than one. But the subset is always the condition. So the P, the if part of the statement, the condition itself, is a subset of the whole statement or the conclusion that comes from it. So it seems backward to a lot of people. So you got to remember that. This says A, if a figure is a trapezoid, then it is a quadrilateral. So they're saying if you've got a quadrilateral, one of the conditions is it would be a trapezoid. So the trapezoid goes in here. So trapezoid is the condition, and then it lies within a quadrilateral, all quadrilaterals. So if a figure is a trapezoid, then it's part of this quadrilateral circle. B, a conjecture is false if a counterexample can be created for that conjecture. Now this one kind of can be challenging to your mind if you're not careful. The English language is very complex, and this sentence is written a little differently. We're used to seeing the if or condition at the beginning, but they put the if right here in the middle of the sentence. So the condition comes after the if. So a counterexample can be created for that conjecture is the condition. So we could rewrite this if we wanted to. We could say if a counterexample can be created for that conjecture, then that conjecture is false. So anyway, just remember that, to look for the condition. But it still doesn't change the fact that the condition, or the if part, the hypothesis goes in the subset of the Venn diagram. The conjecture is false if a counterexample can be created for that conjecture. A counterexample can be created, that goes in here. Created. And if that's true, then it's a false conjecture.